Don't you hate it when you've been here all along and then you start late? Well, it is time to begin. And make sure you, uh-oh. Okay, this should be the right presentation. It didn't seem like it was the right order there, but we'll see. Once again, a reminder about the survey. I didn't check since Monday to see how many more have done it, but I do want everyone to complete it so we can use it to learn, to improve the class. We talked about, well, we did some heat problems at the beginning of last class period, one with conduction and one with radiation. Yeah, so why didn't I give you homework? Because we already had homework on that. And we talked about the greenhouse effect. Today, honest to goodness, thermodynamics, and hopefully getting to some heat engines. And so these diagrams here have to do with heat engines. So first thing for today is work. So work, of course, we've already learned about work in the past. So what's the definition you remember for work? All right, work is equal to force times the distance parallel. So the dot product means the distance parallel. So if that's the definition of work, how do we do that for thermodynamics? Well, we've learned about pressure. Pressure is force per unit area. And so if we have a pressure acting on a surface and then that surface moves, by definition, there's a force times the distance parallel to that force. So this picture here is to illustrate how we come up with the thermodynamic work. So I'm going to look at the force applied to the piston by my gas. So since pressure is force over area, then what's the equation for force? And I know it's written in the diagram. I just want us to think this through. It's what? Okay, so that's just pressure times area. And so that means work is equal to pressure times area times change in distance that is parallel to the area. Now this brings up the first area that could be confusing. I shouldn't have used area there. The first item that could be confusing. I want the direction of motion parallel to the area. What direction do we assign to an area? So if we take this desktop, what direction do we assign to this desktop?
You need direction in terms of force?
No, the direction, we actually define a direction for an area. And it's the normal direction. The normal direction is the direction that's coming directly out of the surface. So my force is in the direction of that area, which is in the direction coming out of the surface. So in this case, I say coming out of the surface because the pressure is pushing on this piston, that force is pushing straight up in this picture. On the wall, it'd be pushing like this. Here, it'd be pushing like this. Remember, force is always putting, or pressure is always putting force directly into the surface. And so if this piston moves because of this pressure, what direction would the piston move just because of this pressure? Up, which is the same direction as the force, right? So if the piston moves so that the gas expands, then A delta X is actually going to be the change in volume that you're adding. Because area times height is volume. And so it turns out this is pressure times change in volume. And because of the direction the force is for pressure, it's always going to be pressure times change in volume. You don't have to worry about any vector things. So for thermodynamics, work is pressure times change in volume. Now this is the work done by the gas. If the gas expands, then the volume increase and it's a positive work done by the gas. So just taking the inverse of that, if the volume decreases, then what do you have for the work done by the gas, positive or negative?
Negative.
Negative, correct, thank you. If it expands, you have a positive work done by the gas. If the gas shrinks in volume, then you have a negative work done by the gas, which makes perfect sense because change in volume would be negative. So pressure always has to be greater than or equal to 0. You do need to use absolute pressure with this, not gauge pressure. So it's always greater than or equal to 0. And if it expands, it's going to be a positive work. If it contracts, it'll be a negative work. Now, we can draw a graph here of pressure as a function of volume. And since work is pressure times change in volume, then if I started here and ended here, pressure times change in volume is there's the pressure, there's the change in volume. If I multiply those together, it's the area. And so just like we did before, for any kind of change, if you take the area under the curve, it's going to tell you what the work was, the thermodynamic work. Now, in the picture down below, did it expand? Look at the arrow. Did the volume increase or decrease? It decreased. It went from higher volume to lower volume. So is that a positive or a negative work? If the volume decreases, is that a positive or negative work?
Negative.
Negative, correct. So if you have a transition where the arrow is going to the left, doesn't matter if it's up or down, as long as it's going to the left, then that's negative work. Whereas in the example here, the volume was expanding, so that's a positive work. So you can look at these graphs and you can make judgments on the work. Now, if you have some unknown function and you just have a graph, use geometry to try to find the area under the curve. So usually we'll give you things that are like straight lines, a PV diagram, and it goes from here to here in a straight line. How would you find the work? Say you have that diagram. This is pressure initial, pressure final, in case you can't read my handwriting there. How do I find the work? What was the general method? Seriously? It's what?
Pressure times change in volume.
Okay.
What's your pressure, your initial and final?
I'm not putting in numbers, just I'm talking about method here. So,
But how would you find just your absolute pressure from?
I'm assuming it's given. So what? I don't just do final minus initial. What I have to do is find the area under here. And so the area under here is not pressure final, volume final, minus pressure initial, volume initial, or anything like that. I'm going to just use geometry. Because I can break this into a rectangle. What's the equation for the area of a rectangle? Base times height. So we have the height here is P final is the height. And we have the width here is V final minus V initial. And so this piece here has an area of pressure initial times V final minus V initial. But then I have the triangle as well. So for the triangle, what's the equation for the area of a triangle? 1/2 base times height. So this has a height of pressure initial minus pressure final and the same width, so plus 1/2 pressure initial minus pressure final times, okay, I didn't give myself enough space, V final minus V initial. And so that's how I would find the total work done. I'm just using geometry to find the total area under that curve. Does that seem simple enough or does that seem complex? I saw a head nod, which could go either way. Okay, I'm glad to hear that. I don't think it's super hard as long as you understand the concept that work is pressure times change in volume. Not change in parentheses pressure volume, but pressure times change in volume. Actually, coming back, oh, that didn't go back, that goes back. One more thing. If I have a transition where I go at constant volume for pressure 1 to pressure 2, how much work do I have done then? Let's say I have 1 liter of gas and I go from 1 atmosphere pressure to 2 atmospheres of pressure. How do I do that? Obviously, I have to heat it up. How much work is done in going from 1 atmosphere to 2 atmospheres for 1 liter of gas? The answer is none, because it's pressure times change in volume. If the volume didn't change, it doesn't matter what the pressure did, there was no work. Because remember, going back to our first definition of work, force times distance parallel. If volume doesn't change, we didn't have a net distance parallel. First law of thermodynamics, right? We're really talking about thermodynamics because we're intentionally talking about the first law. This right here is the first law of thermodynamics in equation form. Now, in Perusall, somebody said, it's like the law of conservation of energy. No, it's not like the law of conservation of energy. It is the law of conservation of energy. The first law of thermodynamics says energy cannot be created or destroyed. And so when we apply it to a system, U is the internal energy. U is the sum of all the energies of all of the atoms and molecules in your system. Delta U, if U is the total internal energy, delta U is the change in internal energy. So what we have here is the change in internal energy equals Q, which is the heat added to the system. So if Q is positive, then delta U goes up because you added energy. Minus W, where W is the heat, the work done by the system. So now this is kind of confusing, and some textbooks reverse this. So you have to be kind of aware. The law is immutable. Energy can't be created or destroyed. But we define work as positive when a gas expands. But when the gas expands, it's doing work on something else, which means energy went out. And so W, a positive W means energy went out, so your internal energy drops if you have a positive W, which is why there's a minus sign there. So you will see some textbooks, if you look around and you're trying to, I don't understand what this textbook's saying, I look at another, you will find textbooks that have Q plus W. And what they've done in that case is define work as the work done on the system instead of the more traditional, the work done by the system. So it's important that you know what the first law is, not just, well, here's the equation. Because if you just have the equation, you can make the sign mistake. Okay, let's go to woo clap. Come on, I'm doing it for Andy. Yeah, now she's with us. Okay, so going to woo clap. We have 4 people in so far. Oh, let me. Oh, that was the wrong one. I thought that was going to be turning on the. Nope. That's the last one of our woo clap things today. Wow, now I've logged out. That's excellent. I am doing things in good order here. I don't know how that happened. But we'll get back there while you're logging in. Maybe. Connecting. Establishing secure connection. It's getting there. Please don't go to the wrong place. Oh, yes, it went to the wrong place.
San Diego, California.
I do want to watch that, but that's the last thing of the day, not the first thing of the day. Okay. So we have 9 people that have made it here. This one here must be the one that's scared. That turned on the QR code. That's all I was trying to do. Sorry, what was that? Claudia?
It still says there's no vote.
Well, yeah, there's no vote in progress. I'm just getting people signed in. Okay, but I will start the vote now. So here's our first question. What variables are related by the first law of thermodynamics? So which variables were in that first law? Okay, we have 6 people, 7, 10, 11. Everyone answered. How awesome is that? I consider it awesome. And we had some variation. So let's look at these one by one. P, V, and T. Those are the variables we call the variables of state. If you know the pressure, volume, temperature, and number of molecules, you know what the state of the gas is. So the ideal gas law is an equation of state. It relates those variables. So if the question had said what variables are related by the ideal gas law, that would have been correct. But it's the first law of thermodynamics. The second set, FPAVM. I kind of made that up. Newton's second law would have been relating like F, A, and M. And I put in PV so we'd have a couple thermodynamic variables. So that one was just a distractor. Q, W, and U, that's the correct answer because the first law of thermodynamics, energy can't be created or destroyed. U is the internal energy. The change in internal energy is the heat added minus the work done by the system. And nobody said energy, kinetic energy, and potential energy, which is great. Next question. Turn off the results. What is the correct definition of Q in the first law? Of thermodynamics. Uh-oh. Didn't quite get everyone in. I know there's a way to restart this, but yeah, let's keep going because of time. So we had 4 people that said that Q is heat added to the system. 2 said it's heat removed from the system, and 2 said heat contained by the system. Now let's start with the big problem. Q is a transfer of energy. So it's impossible to have anything that contains heat. That's not a possibility. So, 2 of you said that. Make sure you rethink what heat is. Because that's, if you have the wrong understanding of heat, it's going to make everything else have difficulties. So then the other 2 options are the heat added to the system or the heat removed. And there is no majority here, but the plurality of 4 are correct. Q in the first law is the heat that is added to the system. I'm sure you know the difference in plurality and majority, right? If we had reached 7, we would have had a simple majority. Next question. Was the definition of W in the first law of thermodynamics as used by our textbook? And most textbooks, but not all. I left this one so you could see by accident. Okay, well, we had 8 answers again. Kind of worried about the 4 that aren't able to get their answers in. So, work, once again, Work is an energy transfer process. Nothing can contain work. You don't have work in the gasoline in your gas tank. You have potential energy in that gasoline, right? It doesn't contain work, just like it doesn't contain heat. So work contained by the system could not be correct by the definition of what work is. So then we have the two possibilities, work done on the system or work done by the system. And the convention of our textbook and the majority of textbooks is that W is work done by the system, which is why you have the minus sign in the first law. All right, back to the presentation. Here's the questions we just went through. This is just an example of using the first law of thermodynamics. Now, the first law of thermodynamics is simple addition, subtraction. So it's not complicated to do. But if you look at the upper picture, you had heat flowing in and heat flowing out. What is Q based on our definitions of what Q is for that upper picture? If we have 40 joules in and 25 joules out, I know it has Q out equals minus 25, and so it's kind of confusing. But if we have 40 in and 25 out, what is Q? Okay, by words, Q is the heat blank.
Leaving.
Not leaving, heat added. Q is the heat added, and so if we take a heat going out, that's just a negative value for Q, which is why they put the negative 25 there, but it's confusing when they have an arrow out and says minus 25. So you have 40 in, 25 out. The net amount in is 15. So Q is equal to 15 joules. They're being added to the system. So now using the same rule, what is work for this picture? Probably figured out by now that it has in the picture.
Work in is equal to -6.
Work is the work out, right? And so 4 in, that's why they have a minus sign there. 4 in is a negative out. So we have minus 4 out plus 10 out is 6 out. And so what is delta U? It's equal to Q minus W. 15 joules minus 6 joules equals 9 joules, which of course is shown right there. But going through the process is much more useful, I believe, than just saying, look, see the equations, moving on. The picture below is definitely different. In the picture below, what is Q? It tells you, but I want you to identify it still. Okay, in the picture down here, Q is 150. Almost. Minus 150 joules because it's the heat added, and that's not added, that's going out. So Q is negative because the heat is going out. And what is the work? Why is it negative?
Only we're coming in and no we're going out, so it's negative we're going out.
Right. Because the work done by the system is going out, and this is coming in. And so then we have delta U is equal to Q minus W, and you see they just put those numbers in, and you have the same 9 joules for the change in internal energy, even though it was very different numbers. The reason we had 2 different examples here is to illustrate that there's more than one way to go from state A to state B. The first way, we added a little heat and did a little work. The second way, there was a lot of work done on the system and also a lot of heat that flowed out of the system. And that result was the same. First law of thermodynamics is basic in lives. And this picture here is, of course, the one I really want to focus on. We consume energy. I eat food. I'm not going to, but I might go to the cafeteria and get free pumpkin pie today for lunch, right? I eat that pumpkin pie. That pumpkin pie has chemical energy that is accessible to my body. My body can use that. And so I'm taking energy in. And as I take that energy in, what does my body do with that energy? Go ahead. I don't know, you just said. Okay, it converts it. It might use that energy to make my brain operate. What kind of energy do you need to make your brain operate? Well, you do need oxygen. Brain does not work efficiently in the absence of oxygen. You actually need sugars to create the. Yeah. And so you need to have sugar to make your brain work. You have other ways your body has energy, though. It will take food you eat and convert it into fat, which unfortunately doesn't make your brain work when the body metabolizes it, from what I understand. Which means if you go on the keto diet, you decrease your brain function. Isn't that good to know? Yeah. Well, the keto diet does work if you pay attention to the first law of thermodynamics. The idea behind the keto diet is that the energy density, well, you have a hard time eating as many calories as you would if you were eating other foods, is the theory.
But also, if you use the keto diet, you're only getting fat and no carbs, right?
Yeah.
And so the carbs don't hold to the water. So you're reducing your water weight initially, but then.
Which is useless, but it makes it look good on the scale. But the key to all this is the energy balance, the first law of thermodynamics. If you take in more energy than you use, your bodies can store that energy in the form of fat. And so you gain weight because your body's storing energy. If you use more energy than you take in, your body's going to burn fat or muscle. Like if you're skinny and you are starving yourself, your body will burn muscle because there's energy stored there, and you'll lose weight. So the whole weight gain loss equation is application of the first law. If you take in less energy than you expend, you will lose weight. Now, metabolism is also a part in this, right? So I'm not just saying if we all eat the same diet, we'll all have the same, percent body fat or something. No. There's other individualized things. But that's an example of the first law of thermodynamics in application. So you can eat high-calorie meals at McDonald's every day and lose weight if you exercise a lot, so you have more energy going out than coming in. But you won't be healthy. You won't be a healthy skinny. You'll just... Anyway. And the same thing goes on in a plant. You have energy from the sunlight coming in, which catalyzes a reaction. For some reason, I can't remember what the name of this. You have chlorophyll, the sun hits it, you have what? I feel so dumb. Photosynthesis, yes. And so you have the energy from the sun catalyzes that photosynthesis so that it then produces energy from what was stored in the plant, what came up from nutrients, for it to survive, and then the plant will also give off energy. So those are applications of the first law of thermodynamics. Now, taking a brief soliloquy away from this topic, this is actually something I mentioned before, but now I have the actual ability to talk about it carefully. When we talked about what temperature is, we said temperature is a measure proportional to the average, and I said kinetic energy. Now I'm going to generalize it, proportional to the average energy of the molecules. And so if we have a monatomic ideal gas means that your molecules are helium, neon, argon, krypton. They're single atom molecules. Then from the kinetic theory of gases, we had that the translational kinetic energy is the only energy present, and it was equal to 3/2 capital NKT or 3/2 lowercase nRT. So the kinetic energy, the total kinetic energy, depends on the temperature, the number of molecules, and then some constants. Now, if I have a process where I have constant volume, I asked you the question when we talked about work, what happens if we went from 1 atmosphere to 2 atmospheres at a constant volume, and how much work was there?
None.
None, because it's P times delta V. Even though the pressure changed, the volume didn't, so there's no work. So if I have a process with constant volume, there's no work. Well, according to the first law of thermodynamics, delta U is equal to Q minus W. If there's no work, then delta U is just going to be Q. Easy enough? Now, U is the total energy. And so this here is the total energy is going to be the total translational kinetic energy for a monatomic ideal gas, because that's all it has is translational kinetic energy. And so my U is 3/2 nRT or 3/2 capital NKT. So if U is 3/2 nRT and I keep the number of molecules constant, then delta U is going to be 3/2 nR delta T. Right? If I change the temperature, then my internal energy is going to change. Temperature doesn't change, there's no change. So that means that for this case, delta U is 3/2 nR delta T, and Q has to be equal to that. And so I have Q is equal to lowercase n, the number of moles, times 3/2 R, multiplied by the change in temperature. Now, we already talked about the specific heat. The specific heat, we had an equation for that was Q equals mc delta T. Y'all remember that? So C was the specific heat. It was the heat per mass per change in temperature. For a gas, instead of doing the mass specific heat, we do a constant volume molar specific heat. So CV is a constant volume, that's why the subscript V, molar specific heat. And so the definition would be N instead of M, because instead of per mass is per mole. CV delta T is equal to Q. And so just matching up those equations, you can see that CV must be 3/2 R. Which is surprisingly or not surprisingly, it's an important result. Now, I also talked about the equipartition theorem. Do you remember me talking about the equipartition? And the equipartition theorem said you have the same amount of energy, 1/2 kT, in every degree of freedom. In every way, the energy can be stored. And for each molecule in a monatomic ideal gas, each molecule can have momentum in the x, y, and z directions. And so each molecule has 3 degrees of freedom. And so your total degrees of freedom would be n times 3. And so if I have n times 3, and I have 1/2 kT in each one, then I get that equation up top that was 3/2 nRT. As a generality, if we have more degrees of freedom, then I should have 1/2 kT for each degree of freedom. So more degrees of freedom means my internal energy, instead of being 3/2 nRT, it could be, for instance, 5/2 nRT. And that constant volume molar specific heat has, coincidentally, 1/2 R to the molar specific heat for each degree of freedom. So for my monatomic ideal gas, it was 3 times 1/2 R was the molar constant volume molar specific heat. This probably to you seems kind of fuzzy.
Yes.
Here is practical data. Well, not practical data. Here's the next slide. This is already established. Remember, I used my pin before to talk about you can have kinetic energy for rotation like this, or rotation like this, but none for rotation like this. That's what this is saying. And so In the case of having rotation for a diatomic molecule, now if it's triatomic, you can have rotation about 3 axes, unless it's perfectly linear triatomic molecule. But we have 2 degrees of freedom for rotation if it's diatomic. And so for translations, we have 3 degrees of freedom, so 1/2 R plus 1/2 R plus 1/2 R. For rotations, we have 2 degrees, 5/2 R. Now let's compare this to reality. So here is a graph showing hydrogen, which is a diatomic molecule, and its molar specific heat as a function of temperature. At low temperature, it's 3/2 R. Why is it 3/2 R at low temperature? It's a quantum physics question. It's because at low temperature, you don't have enough energy for 1/2 kT to equal the lowest rotational kinetic energy possible. And so it simply can't rotate. Which seems bizarre. You're like, what do you mean it can't rotate? It can just rotate really slow, right? That's what classical physics says. But quantum physics says it has to have certain energy levels, and if 1/2 kT is below the energy for rotation, it can't rotate. And so it only has 2 degrees of freedom at low temperature, hence the 3/2 R. But if we heat it up, then it can start rotating. You can see going from about, let's say, 70 kelvins up to about 250 kelvins. It's transitioning. Because now you've reached the beginning of where it can start rotating. You get up to that about, actually it's right about 200 kelvins, so I looked straight on. Get up to about 200 kelvins. 200 kelvins is below room temperature. Then you have 5/2 R, which means how many degrees of freedom does it have now? 1/2 R for each degree of freedom, so how many degrees of freedom? 5, right. It has 3 for translation, 2 for rotation. But then if you get up to around 700 kelvins, then it starts going up again. What would make it start going up again? You have a high enough temperature that there is something adding degrees of freedom. And the final thing is vibrations. And so it will get up to 7/2 R at high temperature because of vibration. And so here's numbers for different gases. So monatomic gases, and of course monatomic ends with argon here. Just draw a separator here so we don't have confusion. That's not argon. That's argon. We're like that. So the monatomic gases, these are real measurements at 25 degrees C for helium, neon, and argon. And you see they're all very close to 3/2 R. Not exactly, because you know what? You have all kinds of things that play into real life that aren't idealized. Diatomics. There's the diatomic ones, and you see those are all relatively close to 5/2. Why relatively close to 5/2? Because you're a high enough temperature that they can rotate, but not a high enough temperature for them to vibrate. And then you go to the polyatomic molecules. Carbon dioxide, that's triatomic. N2O, triatomic. I don't even know I call it dinitrogen oxide, but that sounds really weird. It's not nitrous oxide. Right, that's NO2. And so these have values that are pretty close, but not the same as 7/2 R. Those are going to have more rotational options and more vibrational options as well. So this shows the reality to go with the idealization that we talked about here. So how is this important? Well, as we go in thermodynamics, the CP and CV are important. Now I said CP. What was CV? C with a subscript V, what did that stand for? Constant? Okay, those words are correct, but constant what? Constant volume, molar specific heat. So what would CP stand for probably? Constant pressure, molar specific heat. Now if you have constant pressure, then your work is not zero. And so when you go through and do the math, which I did not doing today, it turns out that for monatomic ideal gas, Cp is equal to Cv plus R. It's not a hard derivation, but we're behind in lectures and I don't have time to go through it. So if you keep the pressure constant and you put in heat, you're going to have the temperature rise by a smaller amount because Cp is bigger than Cv. Question?
Are we going to deal with anything like above monatomic ideal gas in our equations?
Pretty much no. You need to know they exist, but we want to keep things as simple as possible, so we pretty much stick with monatomic.
Okay, so we're just going to stick with like the 3 halves.
For the most part. I mean, you could give a problem where it says Cp is this and Cv is this, and you work with it. But for the most part, it'll be monatomic ideal gases. All right. Oh, that was important. A vocabulary list. In thermodynamics, we have a lot of words to learn. Some of these are going to be familiar, some will be new. So internal energy, I just talked about the sum of the particle energies in your system. Heat, transfer of thermal energy without work. Work is transfer of thermal energy with, changing volume. A heat engine. Heat engine is a brand new thing that I probably won't get to by the end of today. But a heat engine is a device that's sole purpose is to convert thermal energy, that's going to be heat, into mechanical energy, and mechanical energy is work. So the heat engine takes heat and produces something useful for us, work. That's the purpose, and believe it or not, almost everything we use is a heat engine. I mean, your car engine is clearly a heat engine, but our bodies are also heat engines. Then we have a heat pump. A heat pump does not use heat, it pumps heat. So it moves heat. Now we learned the first law of thermodynamics. Today we talked about it. We've already talked about the second law of thermodynamics, which has many different statements, and the one I introduced, the only one we've talked about so far for the second law of thermodynamics, is that heat flows from hot to cold, not from cold to hot. But a heat pump is a contraption that will make heat flow from cold to hot. You have to put in work to make that happen. And so that's what a heat pump does. Examples of a heat pump? Well, an air conditioner. Because an air conditioner will remove heat from a cooler room and exhaust it into a hotter environment. So heat is going from cold to hot because of an air conditioner. Now, as I wrote in reply to somebody on Perusall, a heat pump does not violate the second law. Every step in the heat pump has heat flowing from hotter to colder. But the net result is a net flow of heat from cold to hot. Then we have different types of processes. 4 types of processes. ISO, what does the prefix ISO mean? Same. So isobaric, baric means pressure, barometric pressure. Baric is pressure. So an isobaric process is a process where the pressure does not change. If you're in chemistry, most of your experiments are isobaric. That is, you're doing them open to the atmosphere, so the pressure stays at 1 atmosphere. Isochoric. Choric is a weird word that means volume. So an isochoric process is constant volume. So you see I have also called isovolumetric. Isovolumetric is clearly easier to understand, but isochoric is the standard term. Isothermal. What does thermal mean? This one can be confusing. It's temperature. So isothermal is constant temperature. It's not constant heat, it's constant temperature. That's important to differentiate because adiabatic means heat is 0. Adiabatic comes from, I think it's a Greek word that means doesn't flow. So adiabatic processes, no heat flow. It's also called isentropic because it turns out that if no heat flows, the entropy remains constant. So adiabatic and isentropic can be used interchangeably because the net result of no heat flow is no change in entropy. Finally, entropy. I will talk about entropy later on. Most people have really jumbled ideas of what entropy is. You hear things like entropy is the amount of disorder in a system, right?
Right, that's what it was.
Yeah. But it's not a very practical definition because you don't get the right picture. Yes, Amy?
We're doing thermodynamics right now in Chem 2, and I was so confused last night in lecture because that's exactly how my Chem professor is defining it, is the amount of disorder in a system. And I was like, this is not at all what I'm learning about.
Yeah. So here I have the statement of what entropy really is. Entropy is a measurement of the number of ways you can have the microscopic variables change to have the same macroscopic state. So for instance, the example I always use is rolling dice. If I roll 2 dice, I can get rolls that are between 2 and 12 if I add up all the pips, if they're normal 6-sided dice. How many ways can I roll 2 with 2 dice? 1. And so it turns out the entropy, the equation for entropy is actually really simple. It's really simple, and yet you're not going to be happy with it. It's Boltzmann's constant times the natural log of omega, where omega is the number of ways you can get your state. So for the state of 2 with your rolling 2 dice, there's only one way to get it. So the entropy of that state is Boltzmann's constant times the natural log of 1, which is 0. That's 0 entropy. Now, how many different ways can you roll the dice to get the number 7?
1, 2, 3, 5.
You can have 1 and 6, 2 and 5, 3, and then you can reverse because the way I just say you have a red die and blue die, you can distinguish them. So if the red die is 1 and the blue die is 6, that's different than the red die is 6 and the blue die is 1. So there's 6 ways you can get it. So the entropy of that system is k times the natural log of 6. When you roll the dice, what are you more likely to get, 6 or 1? One doesn't even, what I meant to say was 7 or 2. You're more likely to get 7 because there's 6 different ways you can get it. That's your highest entropy state. And the second law of thermodynamics can be stated that any natural process goes to the highest entropy possible, or goes to raise the entropy. Because if you raise the entropy, you've gone to a more likely outcome. And so really, that statement of the second law is the statistical law that says the most likely outcome is what's going to happen. So that's what the second law is when you talk about entropy. Entropy is how many ways you can rearrange the atoms to the system. Because I've run out of time, I'm going to end on entropy. One final thing. This classroom is filled with gas molecules. And these gas molecules give us a pressure of roughly 1 atmosphere, a temperature of roughly 20 degrees Celsius. Is it possible for me to have a different pressure here and you have a different pressure there?
Yes.
Yes, it's possible. Is it likely? Why not?
Pretty even.
Because the molecules are constantly bouncing off each other and they're going to reach an equilibrium state. They're not going to have pockets of hot and cold. Theoretically, it's possible for all the molecules in the room to be up in the corner for us to all suffocate. That's theoretically possible. But how many ways can you have the molecules distributed in the room and have them all in the corner? Well, it's a small number compared to how many ways you can have them evenly distributed throughout the room. So it's much more likely that we have molecules evenly distributed and we live. So the second law says that's never going to happen for all the molecules to go in the corner because it would be violating the second law, it would be going to a lower entropy state. It could happen in reality, but the probability is so low that no one ever says it can happen. The same argument then goes if you talk about something like creating order from disorder. That is the standard process of evolution, where you start with, well, let's say abiogenesis. You start with some molecules, and then you have those molecules form amino acids. Possible. Then you have those amino acids polymerize to form proteins. Also possible. But, some people say, oh, you're violating the second law because you're going to a lower entropy state. Technically, no, because, well, we can do things like freeze ice. If we freeze ice, that ice has gone to a lower entropy state. But we had to have somewhere that the heat was flowing from out of the ice, and that place went to a higher entropy state. If you take the two together, the total entropy went up. So the same would apply. It's possible to have these steps occur and not violate the second law. You can also make the argument, an embryo growing into a human. We add complexity as we eat food, we poop out waste, and the total entropy is increasing as we go through this. But at the same time, the second law says it's not probable for those processes to occur. And in fact, just to finish up the idea, the environment you need to create the amino acids is the reverse of the environment you need to polymerize them. And so one needs to be low water, one needs to be high water. Making the whole process work would take really a miracle. Okay, we're done for the day. Have a great Thanksgiving celebration if you go to the cafeteria. I'll see you all on Friday.